The part that's missing, that you don't get the luxury of having, is that on the exam, you have to figure out what kind of problem this is first. Like, I'm telling you it's a statics problem today because you know we did statics problems yesterday. This is a direct relationship to what we did yesterday. So you know ahead of time what part of the curriculum we're in. But on your AP exam, you don't get that luxury. I mean, the problem's going to be presented, and you have to decide, of all the things we studied, which part of our study is this. So there are some things about this problem that should tell you to consider statics. The first thing about this problem that should tell you to consider statics is I'm asking for a force. Right away, that should bring up Newton's laws. And Newton's laws are really good at giving you information about force and acceleration. So that's one of the indicators. The second indicator, the object's at rest. So these are reasons why you should know to say, okay, I'm going to do a net force problem, but not just a net force problem where the net force and net torque are set to 0. Now, you might also want to add to your notes that from this point forward, net force problems can also be net torque problems, that we consider both of them. Right? This is not how to solve the problem. This is how to know which part of physics to use for the problem. You understand the difference? Yes? No? Okay, 4 of you do. That's good. Glad to get some feedback there. Now, to solve a net force problem, we know that ultimately we have to decide if it's a first law or second law problem. We've kind of already done that by indicating the object's not moving. So we are starting from the standpoint that these two things are going to be set equal to 0. You'll notice I'm no longer drawing a free body diagram. Part of the reason is because my object has extension, and where the forces act make a difference. So because I need to know that, I'm just going to draw the arrows as they exist right on this object. I'm not going to draw another dot somewhere and say that this is a free body diagram unless I'm instructed to by the exam. Do you guys understand? I'm going to draw the bar, and I'm going to draw where the forces act on the bar. And 2 of the forces are already clearly on the bar. There is one missing. What's missing? The meter sticks weight. So I will draw another force to be the meter sticks weight, and without any intervention, meaning them telling me anything, it's got to be at the center. So if you want a set of steps, I would start with part A. The first thing I would do is deal with Newton's law for force, not torque. Deal with Newton's law for force first. You already have a whole set of steps for that, which generally involved you deciding which law it was, drawing a free body diagram, deciding what direction is positive, identifying the forces that act on the object, and then summing them up in the x direction and the y direction. And those were your set of steps, kind of summarized real fast, right? So that's what I'm going to do here. I've already drawn the arrows. I'm going to say upwards is positive, and then I'm going to identify the forces that act on the object. I have 2 of them. I have tension on the left. I'm going to give it a name. I have tension on the right. I'm going to give it a name. And I have the weight. I know the value of this one. I'm just going to write the value in. And then I will identify which law is important, Newton's first. And I will say net force equals 0. So T left plus T right, they're positive because they are upwards, minus 0.9 equals 0. I've done the net force of the problem here. It does not solve the problem for me. I get to this point, and although I can move something to the other side to help me out, I will notice that I cannot solve for either of these. Together they pull up with 0.9 newtons, but I don't know how much each one does. Any question about that? All right, that's the extent of the Newton's law portion. So for part A, I've dealt with Newton's law. And I didn't write out anything here because we've done Newton's laws first semester. You should be able to reference that. Part B. We have to deal with Newton's laws for torque now. This will be a modified set of things. It'll be similar, and I wouldn't have you redraw this. I'm redrawing it so that we have something to reference, but there's still it's kind of fresh space. Does that make sense? We know that we have TL here, TR there at the 60 centimeter mark, and weight here at the 50 centimeter mark. Now, I kind of presented these steps yesterday, but I'm going to be kind of explicit right now. It's the same kind of thing as yesterday, though. My first question, and this is a question you ask yourself, is it going to be a first law problem or a second law problem? You know, if you want the whole scoop out, I would put that whole question in there. We're only dealing with first law problems right now, but you understand that lasts till the end of the day today, and then we'll start looking at second law problems. So we ask if it's a first law problem or a second law problem. Now ours is a first law problem, so from this point forward, we're dealing with first law. This means net torque equals 0. Now, we have an additional step here that we don't have to do with forces, that we have to do with torque. So not everything's going to be the same, because you can have a first law problem where the object is spinning and a first law problem where the object isn't. It's important that we consider this. We didn't have to do this for force, but we need to know where the pivot point is. So you need to assess now, if it's spinning, you have to use the axis of rotation. I'm not going to write all that. If it's spinning, I guess I am. And I'm only doing it because some of you just won't. So if it's spinning, you have to use the axis of rotation, the one provided. If it's not, I'm going to use this word specifically. If static, you can choose the pivot point. So if you can choose your pivot point, choose a pivot point that eliminates an unknown. That is specifically what I'm doing right now. I am going to choose here as my pivot point. That's exactly what I'm doing. I'm picking a place to make my pivot point. Torque requires it because every torque requires that we know what the torque arm length is, so we need a pivot point. We need to create this point. I could pick anywhere on the object I want. I am choosing this one specifically so that I reduce how many unknowns I'm going to generate in this equation. If I choose any place else, I'll have two unknowns. And I can still solve the problem, but it makes it harder. So choose a pivot point that eliminates an unknown. Like anything else, choose which direction is positive. Do want into the board to be positive or out of the board to be positive? You just have to pick one. It's an arbitrary decision like choosing whether up is positive or negative. So I'm going to choose out of the board is positive. This means counterclockwise is positive and clockwise is negative. That's what that means. So you don't have to use the whole fancy right-hand rule if you don't want to. You just need to pick that things that rotate one direction are positive and things that rotate another direction are positive. Now, nothing's rotating, but this force is trying to cause a rotation in one direction, and this force is trying to cause a rotation in the other direction. So when we talk about torque, we're talking about what would happen if that was the only thing acting on the object. Now, part D, make a chart. Make a chart. We're going to list our torques vertically. Going to sum them. Set them equal to 0. And flesh out each torque based on your pivot point. Again, I can't spell it out any clearer. So I'll make that a little small so I can set that off to the side. I see that there are two torques acting on my object based on where I chose my pivot point to be. There's the torque due to the weight of the meter stick, and there's the torque due to the right-hand string. I'm going to sum those, set them equal to 0. Fleshing out a chart. What's the question? I placed a pivot point there. So by placing the pivot point there, the value for R, which is the distance from the pivot to that torque, is 0. Does that make sense? So that's why it eliminates it. So this chart is a reminder that I need to consider each of these parts of each torque. So set up my equal signs here. Let's start with direction. The first torque is going to cause the object to spin clockwise. Use my right-hand rule, that's into the board. So that's going to be a negative torque. I'm going to put a negative to get started. The value for R is the distance from the pivot to where the weight acts. That's at the middle of the meter stick. That's 0.5. Size of the force was given to me, 0.9 newtons. And it looks to me like it acts straight down, which is perpendicular to the torque arm. That'll be sine of 90 degrees. I have completed that torque. I'm going to flesh out each of the torques the same way. The next torque, upwards, causes a rotation that is out of the board, counterclockwise. We said counterclockwise would be positive. The distance from the pivot point to that torque is 0.6. The size of the force acting at that point is unknown. Use a placeholder. And it acts upwards. I believe it's at right angle compared to my torque arm, so sine of 90 degrees. Now, just like force, all Newton's laws will actually do are generate relationships. This one generates a relationship. That relationship could be used to solve your problem. So let's generate this relationship too. This relationship will be, let's see, 0.5 times 0.9 is negative 0.45 plus 0.6 TR. That equals 0. That's it. That's all Newton's laws do. They generate a relationship. So now we have two relationships. We have this one from Newton's laws, and we have this one from using torque. So TL plus TR equals 0.9, and 0 equals negative 0.45 plus 0.6 TR. So all the work we did was just to get these two things and see if they will tell us what TR and TL are. And they do. And if I solve this, I'll get TR equals 0.45 divided by 0.6, which is 0.75 newtons. Got the unit, it's wrong. I can substitute that back in here to figure out TL. So I need something that will add up to give me 0.9 from 0.75. That's going to be 0.15 newtons. That's all there is. But I say that's all there is. It's not a small amount of things to do, even for one that is simple. Good question, so it's worth exploring. Each torque is applied individually or independently. So when I'm thinking about this force, I'm only thinking about the torque this force causes. So at that moment, when I'm doing torque is R times F times the sine of the angle, this angle, this portion, is just about the torque arm, which is this R, and the force, which is this direction. Those are the only two things I'm thinking about in that moment. When I move on to the next torque, I will ignore that and look at just what's happening to the other torque. And I'll look at that angle. So they can be any which way. I don't have to have them so perfectly lined up and down. In fact, like I said, one of the examples we're going to do today doesn't have them like this. My whole boom, or my whole meter stick could be at an angle. That would make all of them different. Does that make sense? Okay. Yeah.
Going back to the part where you find like tension for the weight of the meter stick, like at the chart, you don't multiply for the force, you don't multiply by gravity because you're already given the weight in newtons, right?
Right. Okay. Right. That's why we didn't need 9.8 here. All right. Want to try another one? I think we should. All right, so I've created a new one. Couple of cinder blocks on the ground. This is like one of your homework questions. A couple of cinder blocks on the ground. I put a big 10-meter long plank on top of the cinder blocks and a guy standing on it at the very center. But the cinder blocks aren't in the middle. All right, I have one cinder block 2 meters in and one cinder block 3 meters in. Everybody see what I've got here? I'd like the force from the cinder blocks on the plank. This won't be a tension, this will be a normal force. There'll be 2 of them, one from the left cinder block and one from the right cinder block. Okay? Now I gave everything in kilograms this time, so you will have to use 9.8 to get them in newtons.